Thank you everyone for being here. I'm Qi. Today I'm going to talk about how to using learned predicate to optimizing query executions. This is a joint work between Georgia Tech, Gauss, and Alibaba. Today's presentation is going to be three parts. First, I'm going to talk about the motivation of this work. Then, I'm going to present the overall approach of this work. In the end, I'm going to present the evaluation result of our SIA system. So we start with the motivation. Here it's a query from TPCH benchmark. It joins two tables, line item table and orders table, on their join key, order key. And I want the audience to notice that any column name start with O is from orders table. Any column name start with L is from line item table. So after doing the join, this query applies three additional predicates on the join table. The first predicate is ship date minus order date less than 20. The second predicate is order date is happened before 1993 June 1st. And the last predicate is commit date minus ship date is less than ship date minus order date plus 10. If we input this query into Postgres will generating the following logical plan. Because the predicate order date happens before 1993 June 1st, only using columns from orders table, the Postgres optimizer actually pushed this predicate down to orders table before the join. And after the join, the Postgres will apply additional two predicates. Both of these predicates refers columns from line item table and the orders table. Thus, both of these predicates cannot be pushed down to any tables. However, we can also rewrite this query to another semantic equivalent queries Q2. The only difference between Q1 and Q2 is Q2 has three additional predicates. All of these three additional predicates can be inferred by the original predicates. For example, one of the additional predicates is ship date is happened before 1993 June 20th. This is inferred by the predicate that ship date minus order date is less than 20 days, and the order date is happened before 1993 June 1st. The ship date has to happen before 1993 June 20th. The other two additional predicates can be inferred by similar way. Thus, we know that Q1 and Q2 are semantically equivalent. However, if we input Q2 into Postgres, we get a different logical plan. And the major difference is all these three additional predicates are only using columns from line item table. Thus, they can be pushed down below join to line item table. And the others are similar as Q1 logical plan. If we both executing these two logical plan in Postgres on TPCH dataset with data scale factor as 1, we find out that the second logical plan actually execute 2 times faster than the first logical plan. And the reason is these three additional predicates being pushed down to line item table actually filter out a large portion of tuples that are unnecessary from line item table to do the join operation. And by rewriting Q1 to Q2, a semantic query, we actually get a better execution plan that are 2 times faster. So the key insight is here. The first key insight is by synthesizing weaker predicates for a given set of columns, we actually can possibly enable additional optimization rules that previously are unapplicable. And one example would be that the ship date is less than 1994 June 20th because this predicate only using columns from line item table and it can be pushed down to line item table. And the second key insight is that to synthesize a valid predicate, we need to synthesize a valid predicate that filter out the most number of tuples. Not arbitrary predicate going to be very helpful in speed up the execution. An example here is that if we can synthesize ship date happened before 1993 June 20th. It's better than we synthesize predicate ship date happened before 1994 June 20th because the first predicate can filter out more tuples. Now I'm going to present the overall approach. So we first want to formally define our problem. So we first define what we mean a valid synthesized predicate. So given an original predicate P1 that only refers columns in set columns 1, and a subset columns 2. We want to synthesize a predicate P2 that only using columns from the subset and also weaker than the original predicate. What do we mean by weaker? So basically, any tuple that is accepted by the original predicate should also be accepted by the new synthesized predicate P2. In this case, we call P2 a valid synthesized predicate. We then also want to define what we call an optimal predicate. So an optimal predicate is a valid synthesized predicate that filters out the most number of tuples. Here is an example. So suppose the original predicate is A1 minus A2 less than B1 and B1 plus 5 is less than 10. We want the new predicate only using columns A1 and A2. Then a valid predicate can be A1 minus A2 less than 100 because it can inferred by the original predicate. But the optimal predicate would be A1 minus A2 less than 5 because there is no other valid predicate that reject more tuples than these predicates. So now how we can synthesize such predicates? If we view the predicates more closely, we will find out that a predicate is actually a binary classifier. It separates tuples into two different kinds. The tuples is going to be accepted by the predicates and the tuple going to be rejected by the predicate. So machine learning actually, training a binary classifier is actually a very standard problem in machine learning. So if we can leverage the machine learning algorithm to train a binary classifier, then we basically get to the predicates. However, there are three questions we need to answer before we can use machine learning algorithm to synthesize such predicate. The first question is how we can guarantee the predicate is valid, right? How do we know the synthesized predicate is actually weaker than the original predicate? The answer is we can use the SMT solver. So SMT solver called satisfiable module series solver is a standard symbolic reasoning technique that widely used in program language community. It turns out we can use SMT solver to reasoning that the rewritten query is actually equivalent to the original query to prove that the predicate is actually valid. And the second question we need to answer is how to generating training samples, right? Because the new synthesized predicate doesn't exist yet. How do we know which tuple should be rejected by the valid predicates and which tuple should be accepted by the valid predicates? We actually define what we call unsatisfaction tuple, and we prove that all unsatisfaction tuples should be rejected by the optimal synthesized valid predicates, and all satisfaction tuples should be accepted by the valid synthesized predicate. And we encoded this unsatisfaction tuple into a formula and leverage the SMT solver to generating training samples. And the last question we need to answer is how do we achieve efficient learning, right? Because as we said, not arbitrary predicates are going to be useful. We have to generate the predicate that's close to optimal. And it turns out we can use what we call the counterexample guided learning loop, which I will explain in the next slides. So here is the counterexample guided learning loop. At the beginning, we were using the SMT solver to generating the true samples and the false samples, and we enter into the learning phase. After the learning phase, we will get a candidate predicate P1, and we will use the SMT solver to verify if the P1 is a valid predicate. If P1 is not a valid predicate, the solver will give us a tuple that should be accepted by the valid predicate, but is rejected by current candidate predicate P1. We call these true samples as counterexamples. We added these counterexamples into the true training sample set and start the next iteration training. If the candidate predicate P1 is valid, we then trying to verify if the predicate is optimal. If the predicate is not optimal, then we can also find a counterexample as false example, which means the tuple should rejected by the optimal valid synthesized predicate, but is currently being accepted by the predicate P1. In this case, we added this counterexample into false training sample and start the next iteration learning. And if we successfully verify the current candidate predicate P1 is valid and optimal, then we just output this predicate. Or if we hit the maximum allowed number of iterations, then we just output whatever the current valid predicate P1 is. So here is Here I'm going to explain how we actually generating the training samples. Suppose the original predicate a1 minus a2 less than b1 and b1 plus 5 is less than 0, and we want to generating a predicate that only using columns a1 and a2. And then we can define what we call unsatisfaction tuple based on the original predicate and the given columns. As we can see here, if we assign the value 17 to a1 and 4 to a2, then no matter what's the value for b1, the whole tuple cannot satisfy the original predicate. I want to emphasize here that for all possible, there is no possible value for b1 such that if a1 equal to 17 and a2 equals to 4, the whole tuple satisfies the original predicate. And we call this unsatisfaction tuple. And we actually proved in the paper that all unsatisfaction tuples should be viewed as false samples because they should be rejected by the optimal synthesized predicate. And then we also have the concept satisfaction tuple. So satisfaction tuple, here is an example. If a1 equals 5, a2 equals 4, then if b1 equals 2, the whole tuple should be accepted by the original predicate. We want you to notice here that if there is one value for b1, such as 2, to make the whole tuple satisfied by the original predicate, then the whole tuple is satisfaction tuple. And we proved that all satisfaction tuple should be accepted by a valid synthesized predicate. So all satisfaction tuple can be used as true samples. And here is how we encoded these conditions into formula. So given a predicate P1 that uses columns in set columns 1 and the subset columns 2, the true samples can be encoded in the following formula. So P1 stands for the original predicate. Not old is a set of formula that force the SMT solver give us a new model, so it's not repeating itself. So if we input this formula into the solver, the solver will return a model, which a model is a satisfaction tuple, which we can be used for true samples. And the false samples is a little bit complicated because we need to encode for all unsatisfaction tuple, but it has the similar structure where not old is used to force the solver to give us the different samples each iteration, and the for all columns 2 in columns 2 not P1 actually encoding that there's no possible values for columns not in the subcolumns actually makes the original predicate satisfied. And after that, if we feed this whole formula into the solver will return a model, and each model is an unsatisfaction tuple which can be used as false samples. So after we get true samples and false samples, we can enter into learning phase to get a candidate predicate. But we need, as we said before, we need to verify if the candidate predicate is valid and optimal. So how do we do that? For verify validate predicate is pretty simple, right? We just leverage the SMT solver to verify that P2 actually implied by P1. If it is not, then we were generating counterexample that P2 is accepted but not accepted. P1 is accepted but not accepted by P2. In this case, we can view this counterexample added into true sample start next iteration learning. So how can we verify optimal? So optimal is the predicate that should reject all unsatisfaction tuple. So we encode this formula and feed into the solver. If solver returns a model, then there's an unsatisfaction tuple is accepted by current candidate predicate. So we can edit this unsatisfaction tuple into false training sample and start the next iteration. Then I'm going to use the example to demonstrate how counterexample guided learning loop works. So the given predicate is a2 minus b1 less than 20, and a1 minus a2 less than a2 minus b1 plus 10, and b1 less than 0. The given columns is a1 and a2. In the first iteration, we first generating sets of false samples and true samples. As you can see in this graph, true samples are blue circles and the false samples are red triangles. We then use the machine learning algorithm to learn a binary classifier. The binary classifier we learned is A times 2 times A1 plus A2 plus 50 greater than 0, which is the black line in the graph. And you can see this black line perfectly separates false samples from the true samples. Then we then verify if this learned predicate is valid, and we find out it's invalid. So we can generate counterexamples which marked as yellow diamond. These counterexamples should be classified as true samples, but now they're being classified as false samples. So we added these counterexamples into true sample set and start the next iteration learning. After we do that, we learn a new predicate, A1 minus A2 plus 32 greater than 0. As you can see here, this new predicate completely separates false samples with true samples. We then verify if this new predicate is valid, and it's indeed valid, but it's not optimal because we can generate counterexamples which is marked as yellow diamond. These counterexamples should be classified as false example, but currently is being classified as true samples. So we add these counterexamples into false sample set and start the next iteration learning. Then in the final iteration, we actually learn a predicate which is A1 minus A2 plus 29 greater than 0. And we actually can verify this predicate is valid and optimal. So we finish the learning process and return the predicates. The last question we need to answer is what kind of machine learning algorithm we're going to choose, because there are so many of them. Basically, we have 3 requirements for the machine learning algorithm. The first one is because we're training a binary classifier, so we have to use the binary classifier algorithm. And the second one is because we need to convert back the binary classifier to the predicate, so the model has to be interpretable, so we can express them in SQL predicates. The last one, and also a very important one, is we have to guarantee the model is verifiable, because we need to leverage the SMT solver to verify that the learned predicate is actually weaker than the original predicate, so it's valid. We're currently using linear SVM because it satisfies its 3 properties, but we are open to other choices as long as they satisfy these properties. Okay, so in the last part, I'm going to present evaluation. We're trying to answer 2 questions by our experiment. The first question is this approach more effective than syntax-driven approach? Our baseline is transitive rewrite rules. And the second question is, does this approach actually improve the query performance on real data? To answer these 2 questions, we're randomly generating 200 queries derived from TPCH benchmark by using the following templates. We always join 2 tables, line item table and orders tables, and randomly generating a conjunction of predicate. Each atomic predicate always refer columns from line item table. Thus, it's impossible to push down any predicate to line item table. We choose to use TPCH as our benchmark because both data and query are publicly available. We compare our system SIA to the transitivity rules, and we find out that for less complicated predicates, the predicate only contains 1 column. SIA is able to generating 182 predicates out of 233 predicates, while transitivity rules only able to generate 15. And it's even more significant when the predicate contains more number of columns. SIA is able, for example, SIA is able to generating 102 predicates out of 116 possible predicates for 2 columns. To answer the other question, is this actually improve the query performance in real data? We find out that our C system is able to rewrite 114 queries out of 200 queries, and we run both original queries and rewrite queries on latest Postgres. When we set the TPCH data scale factor as 1, we find out that 85 rewriting queries are faster, 36 rewriting queries are actually 2 times faster. When we set the data scale factor as 10, it's more obvious. 95 queries are faster, 66 queries are 2 times faster. To summarize my presentation, I present a system that using learned predicates to speed the execution of queries, and the evaluation shows that this approach can speed execution of queries in practical data. Thank you.